test.
Okay. Hello everyone. My name is Yuding. I come from Norwegian University of Science and Technology. Today I will give the presentation named, as you see, Hydrogen-induced transgranular to intergranular fracture transition in bi-crystalline nickel. Since you have given so many wonderful experimental works about hydrogen enrichment from the aspect of experiments, so here I will focus on a different aspect by using atomic modeling here. And as you know, hydrogen embrittlement is an old topic since 1 century ago. Recently, it raised numerous attention due to the popularity of hydrogen as a clean energy for the future. However, the problem associated with hydrogen storage and transport are substantial. The phenomena that diffuse hydrogen into metals causing catastrophic degradation of the mechanical properties known as hydrogen embrittlement. It usually results in premature failure and cause heavy economic loss. Since first observed, many mechanisms have been proposed. Here I list 3 famous ones. The first one, hydrogen-enhanced decohesion, just a heat mechanism, where the research assumes that hydrogen segregated at the green boundary or the crack tips weaken the atomic bond and cause a reduction of fracture energy. The second one is hydrogen-enhanced localized plasticity, where hydrogen shares the elastic field of dislocation and then enhance the mobility. And it also have different different shape in current version. It have so many versions. The third one is hydrogen-enhanced string-induced vacancy. Just hydrogen could cause a superabundant vacancy formation, and which is responsible for the subsequent nanovoid nucleation and coalescence. All of those mechanisms could give good explanation to certain experimental observations. But however, when it comes to nanoscales, the detail about how those mechanisms works are still unclear. In other words, the direct interaction between hydrogen atoms and their microstructures are still missing. Due to the reason, you know, that hydrogen is so hard to track directly in the experimental observations. So to address these questions, we utilize the multi-scale modeling here, or specifically atomic modeling here. The molecular dynamics, the method we use here, basically we only need 2 things. The first one is Newton's law. The second one is the interaction between hydrogen atoms and metal atoms, which is usually obtained by first principle calculation or by fit the experimental result. You can imagine in molecular dynamics, there is a million, even billions of atoms. They interact with each other according to the interaction that get obtained from the first principle. And by investigate the interactions between hydrogen atoms and the metal atoms, we can get insight into the nanoscale hydrogen embrittlement interactions. So this is where we are and where we're from. Come to some details about the simulations results. First, you can see we pay attention to the hydrogen embrittlement in a single crystal nickel. This is a perfect nickel, means there is no defect, no initial defect inside it. This is around 2 million nickel atoms, and then we randomly charge the hydrogen into the samples and do the tensor test. As you can see in the left figures, this is the strain stress curve with different hydrogen concentration. The black one is a pure nickel, and the different colorful lines represent the nickel with different concentration of hydrogen. The nickel hydrogen 0.001 means that for every 1,000 hydrogen every 1,000 nickel atoms, we only have 1 hydrogen atoms. And as the hydrogen concentration goes up, we see the softening effect. But this is something not common we usually see in the experiments, because we only see the softening effect only in this green line, and this is have a hydrogen concentration around the nickel hydrogen 0.1. This could be already regarded as the nickel hydride, and this is something intrinsically unrealistic, because we know that in experiments we could have embrittlement with a very low hydrogen concentration. So this tells us more attention should be paid to hydrogen interaction with defect, where there could be a very locally high hydrogen concentration. And then we come to the green boundaries we focus in our studies. In these samples, we built a bi-crystal. You can imagine in the middle of the sample there is a green boundary here, and in other part it's the green internals. And we choose 3 types of green boundaries: sigma 3 coherent twin boundary, which is famous for its resistance to hydrogen embrittlement, and sigma 5 symmetry tailed green boundary, which is a typical high angle green boundary, and the sigma 9 green boundary is a twist boundary and could be a representative of the general green boundary. And we use a Monte Carlo method to charge the sample according to the different segregation energy at the green boundaries and the green internals. And here is the equilibrium hydrogen distribution in the samples. You can see in the middle it's the green boundary, and in the green internals it's the perfect FCC nickels. And you can see the black dots is the hydrogen atoms. It's mainly distributed as the green boundary area for the sigma 5 and sigma 9 green boundaries. And this figure B is the local structure just from the green boundary area region. And the sigma 3 have less ability to trap hydrogen, just as the experimental work shows. And here the basic conclusion is very simple. Just the green boundary works as a preferred site for hydrogen trapping. And according to the Monte Carlo method, we get a precise distribution of the hydrogen atoms around the green boundaries. Then we carry out subsequent mechanical test to utilize the uniaxial stringing here to mimic the area near the crack tip where the hydrostatic stress is high. And as you can see, could you play the video? Yeah, this is during the tension, you can see the samples without hydrogen and with hydrogen. This red atoms represent the HCP atoms, which you could regard it as the plasticity activities in the samples. And could you? I'm sorry. I'm not familiar with this pen. So this part is you can regard as the vacancy concentration at the green boundaries. And you can see during the tension, as the string goes, more plasticity happens in the greens, and more vacancies formed at the green boundary. And finally, the void nucleation, nano-void nucleation at the green boundaries. And for the cases without hydrogen, it nucleates in the green internals. This shows that this is directly the observation of a hydrogen-induced transgranular to intergranular fracture transition, as the nano-void nucleation has transformed from the green internals to the green boundaries. So we regarded this process as just as our presentation's name, hydrogen-induced transgranular to intergranular fracture transition. Then we come to some deeper analysis of this process. Here is a strain stress curve that shows corresponding to the animation. You can see here is the strain stress curve. The green ones is the cases without hydrogen. The pink ones is the cases with hydrogen. You see many curves here because we carry a lot of simulations with different temperature set. That means we could get a statistical reliable result from our simulations. And the two main differences between the cases without hydrogen and with hydrogen is that first, the stress for dislocation nucleation has been highly decreased. Just here, you see, just at this point, the snapshot shows the moment corresponding to this stress. This just directly shows the evidence that hydrogen highly enhances the dislocation nucleation. And another feature when hydrogen charges is the earlier formation of a nanovoid. You can see here the nanovoid for the cases without hydrogen is formed in the grain internals. And we regard this reduction of stress as the loss of ductility. And this loss of ductility is always combined with the transgranular to intergranular transition. Just the nanovoid nucleation site has transferred. And we come to some deeper analysis. Why this happens? We analyze the stress distribution, just the von Mises distribution in the samples. You can see the figure B without hydrogen, the figure C with hydrogen. And the axis position in Y means the sample in Y direction. When the position is near to the 0, it means the grain boundary region. And when the position is far from 0, for example, just 100, it's the grain internals. You can see when there is no hydrogen, grain boundary works as the grain boundary could release the stress concentration at itself during the deformation. However, when hydrogen exert, it inhibits the grain boundary's ability to relieve stress and even cause a local stress concentration. And we think this hydrogen-induced stress concentration that causes the subsequent earlier dislocation nucleation and nanovoid nucleation. And here we do some specific focus on the dislocation grain boundary interactions and vacancy grain boundary interactions. Just we want to verify what is the key rules during this transition. It's dislocation, it's vacancy, or it's grain boundary, or it's the core effect of them. And the figure A shows the cases without hydrogen at the moment before plasticity happens and after plasticity happens. This figure B also shows the cases with hydrogen before plasticity happens and after plasticity happens. And you can see here, when there is no hydrogen and no plasticity, vacancy concentration at the grain boundary is limited. When plasticity happens, the dislocation interact with the grain boundary, leave a not so obvious line-shaped vacancy cluster on the grain boundaries. For the cases with hydrogen, when there is no plasticity, hydrogen don't make sense. But however, when hydrogen exert, it play as a dramatically amplify for the dislocation grain boundary interaction and formed a very clear line-shaped vacancy cluster on the grain boundary. And we throw these figures, just the figure D, you can find here. The red curve represents the plasticity activities in the grain internals with or without hydrogen. You can see when hydrogen exert, the dislocation amount didn't change much. However, the vacancy concentration in the grain at the grain boundary has been raised by up to 10 times. And we think here that the vacancy concentration at the grain boundary must play a very key features during the transgranular to intergranular transition. So we carry out more cases with different temperature, different hydrogen concentration, different grain size. We carry more than 1,000 simulation or 1,000 cases. With each case repeat more than 20 times. And we collect just one example here, the relationship between the hydrogen concentration and the vacancy concentration. We can find that, and we also show during the strain how the vacancy concentration evaluate with the strain. We find that when the strain go up, the vacancy concentration go up. When the hydrogen concentration go up, the vacancy concentration also go up. And for the lower temperature, the vacancy concentration is also enhanced. And we always find the highest vacancy concentration with the highest hydrogen concentration and the lowest temperature. Then we collect all our results into those pictures. This is the main result. And we can always find that when the vacancy concentration reach a critical value, there are always a fully intergranular fracture. What does it mean, fully intergranular fracture? This means that if we have 20 samples, 10 of them filled with transgranular, 10 of them filled with intergranular, we regarded the intergranular fracture fraction as 15%. And we collect all our data, regardless its hydrogen concentration, regardless its temperature, regarding its grain size. We only focus on the grain concentration and the intergranular fracture fraction, and we get this, just the S-curve here. When the vacancy concentration at the grain boundary is low, transgranular dominating, and when the vacancy concentration is high, fully intergranular fracture happens. And the conclusion is here, just this transgranular to intergranular fracture transition is directly given by the vacancy cluster formation at the grain boundary. And a fully intergranular fracture model will reach when the critical vacancy concentration is reached. And those findings should make the quantitative prediction of hydrogen-induced intergranular fracture possible, and will be further talked in the plenary speaker by Professor Zhiliang Zhang in the Tuesday. You can pay attention to that. And this is the conclusion of the take-home message. Sorry, I just take too much time. The first one is just a direct demonstration of hydrogen-induced transgranular to intergranular fracture transition directly observed by optimistic simulations. The second one is a quantitative relationship between the intergranular fracture fraction and the vacancy concentration based on a statistical result. And that's all. Just take too time. This is my colleagues and my co-authors. Thanks for my labs.